very easy, no calculation involved in it. What I want you guys to understand, the switching and the receptacles, I always say at least 30% of any project that you're involved is going to involve some type of receptacle, unified receptacle, and some type of a switching mechanism. Cool? That's what this chapter is all about. Switches and receptacles. So let's go ahead and see what we're going to be covering. So switches, receptacles, rating for particular application. Every time you have a switch or receptacle or any piece of equipment, Joe, that you installed in electrical system, you're guaranteed it's going to be rated for at least what? Anybody knows? What do we do when we power things with what? Voltage, right? You need to have, it's going to be rated for voltage, right? Second, what's next to the voltage? Amps, right? And third, most likely is going to be, do we deal, which is not commonly used, but it's becoming more and more common now, is it AC or DC? Is that switch or the receptacle rated for AC or DC, right? 99% of what we do right now is, or 95, 90%. It's changing now with the photovoltaic. 90% of our systems are AC systems, so we don't worry about this one, but it will be AC, DC things. Different type of receptacles, 50 amp receptacle, 28, 120 versus 120, 15 amp receptacles. So there's so many variation, guys, of receptacles. I'll tell you stories when we get into the NEMA type receptacles. When it comes to the switches, most of the time you deal with single pole switches. You're looking at them right in here. These are single pole switches. You can also deal with double pole switches. Double pole switches can switch 2 phases, or 3 pole switches sometimes that can switch 3 phases. And you can deal with 3-way and 4-way switches, which you guys are familiar from the residential. I want to give you an idea. In a commercial building, there isn't a whole lot of 3- and 4-way switches. Because of the energy code right now, we don't use a whole lot of 3- and 4-way switches. Adam, when you get into the commercial building, the first thing you want to get out of your mind is 3- and 4-way switches. Cool? There are not a whole lot of 3- and 4-way switches. The reason for this one, Darren, because we use occupancy sensor that since people are moving, turn the light on to save energy, right? And also we use low voltage switching, which eliminate the need for 3- and 4-way switches. Can I have a thumbs up, Chubb? When it comes to commercial building, 3- and 4-way switches, not a whole lot used. Cool? So these are what we're going to do about receptacles. So a couple of things. Select switches or receptacles with a proper rating for the application. Install various type receptacles and 3- and 4-way switches. NEMA, thanks God, came up with a list of NEMA rated receptacles that you guys have seen this before. You rated them before. NEMA 15-20 or whatever. You're going to look at the NEMA configuration for receptacles. Receptacle guys are weirdos because they can go different voltages, different amps, right? You can have a receptacle that run at 480, 277, 50 amps, 3-phase, and a receptacle that, like that one that you're looking at, 15 amp, 120 single phase receptacle. Cool? So NEMA has a bunch of receptacles waiting for it. Develop the standard, thanks God for this. You're going to have a receptacle and a plug, and we'll look at these. I know we went through this one. NEMA rated them based on what's the receptacle what's the plug that matches the receptacle. You're looking at that one right up there. And these two guys are rated based on the most important 2 quantities that we as electrical engineers and electricians deal with, right? What's the most 2 quantities that we measure? The voltage and the current, right? The voltage and the current. So all these plugs and receptacle are, the rating is going to be based on voltage, what's the highest voltage you can put in it, and what's the highest amp they can put in this receptacle. There's also something called hospital grade and commercial grade receptacles. When it comes to receptacles, Jeff, you know that, and the ones who install them, do you guys know that the receptacles, I should have brought one, I'll bring them in my office. They're receptacles, 15 amp and 20 amp receptacles that you can buy for $1.30. Tamper resistant receptacles, $1.30, and they're receptacle that costs you $5, $6. So what's the difference? Both of them look exactly like this point here. Both of them, the receptacle that we use in residential are called residential grade receptacle. They're cheap, they're manufactured cheaply, meant typically for residential. The receptacles that we use for a commercial building, it's called spec receptacles. Right there, and when you guys work with the hospital or in any other commercial building, most of the time, engineered projects like the one they're going to do, it's going to be called spec receptacle. Spec receptacle are look exactly like the other receptacles, except they're made more robust, stronger, better. So plug and unplug things. They're not gonna. They live longer. They don't arc. They don't fail on you. They're not the ones that you stab from the back to put the receptacle to put the wire in. So they are a better quality receptacle. Can I guys get you to understand there are two types of switches and receptacles? There's the cheap ones that we use for residential, and there's the expensive one that we use for spec, for commercial industrial. Everybody is cool with that? When you do the takeoff for me, you're going to do the ones called spec receptacles. These are the expensive ones. With this comes also hospital grade receptacle is one type of spec type receptacles. One type of spec type receptacles, as you said, where severe abuse is used. We use them a lot in hospitals too. Heavy use expected. So when it comes to receptacles, can I get you guys to use spec type receptacles, the one that we use, which is more expensive, more robust, can handle more abuse. Everybody's okay with that? Receptacles and switches. Cool. So that's the thing that I want to do. Hospital grade receptacles they look exactly the same like a 15 and 20 amp receptacle. They act exactly the same, rated exactly the same in terms of amp voltage. The only difference is they can handle heavy. It's like my Suzuki for that I used to have, my Suzuki car versus your Ford big F-250 now. Is it 250 truck? Right? They both do the same thing. Jeff comes from Bloomington with his truck, right? I'm going to pick on you. F-250, and Chad used to come with his Suzuki, that little Suzuki. Both of them do the same function, but which one is better? You can sit here and argue, but which one can you survive an accident then? Okay, does that make sense? The spec receptacle and switches versus non-spec. So, Kerry, my friend, when it comes to a commercial industrial building, moving on right now, you're going to forget the residential grade receptacle. These cheap little ones, 33 cents or $1.30 for their timber. We're going to forget about them. We don't install them. Can we install them, by the way? Can we install these in a commercial building? Yes, the code doesn't care. An engineered project, a good engineered project will eliminate them. How do we eliminate them, Joel? With the spec. The specification that coming from the engineer, they always say commercial grade spec receptacles, meaning we want the heavy duty type 15 and 20 amp receptacles. Can I have thumbs up, Chad, for you understand that one? Okay, for receptacle, guys, there are most of receptacles, the most convenient, the most used receptacle have three terminals. You guys are familiar with that. One terminal is going to be for the ground, and either it's going to be labeled with G, GR, GN, or ground. And this is or green colored terminal. That's your ground, right? The second one is silver, and that's going to be for what? The white conductor, or labeled with white. That's the grounded conductor. And the third one is going to be brass, and that will be for phase A, phase B, and phase C. You don't have to memorize this, but when you're looking at a receptacle, any terminal that green is going to be for grounding conductor. Any terminal that's silver, it's going to be what? For what? For white conductor, which is a grounded conductor. And any terminal that red, the brass is going to be for any of these hot conductors. Any of these hot conductors. So this is what you're looking at, my friends. How do you draw that little, and this one here. Here's my typical receptacle. So that's basically what we're doing. So ground is going to be right here, right? And then we're going to have the hot is going to be right in here, and the grounding is going to be right in here, right? So here's your ground, here's your hot, here's your neutral. The worst thing that could happen to any one of us is you don't know which side is the hot. Again, most of you guys are not electricians, but at least when you walk into a receptacle like this, you should know which side is the hot. I know you're not troubleshooting things, but it's really as a designer, Kerry, walking in there, and there's a problem in the receptacle, and they want to ask you, where should I start? Some electrician, smart aleck like Darren, for example. Oops, sorry, Darren. Will ask you, hey, Mr. Engineer, where should I start troubleshooting this receptacle? Maybe you should at least know the configuration. Does that make sense, guys? It makes you a better designer? Better designer to know the configuration. Any question, guys, about this? This is the most convenient receptacle you're going to encounter. The 15 amp, 120 volt. And the labeling on them. Can I have thumbs up, Chad? We fully understand this. And this is new, not new to all of you. There's also electronic, if you have electronic equipment receptacles, we'll talk about electronic equipment receptacles. Receptacles for cashiers. When you go to Home Depot, guys, and they slide your credit card, and they get the money out of your credit card and all this good stuff, banks and all this stuff. These, they need, long story short, they need a clean ground. They need a clean ground. That's why they call them electronic equipment receptacles. They use two things for these receptacles, guys. They give them a dedicated, fully insulated grounding conductor that goes all the way to the surface. Can I have thumbs up, Chad? Special. Why would they do that? Because of noise. What's noise? Everybody knows. You know what noise is? If I type on my screen Chad, if I type Chad and on my screen it shows Aaron, that's a noise. That's that's a faulty equipment. So noise. So to reduce noise in the circuit, loads for computers, we do the computer sensitive electronic equipment should be, and here's the key point, isolated grounding receptacle. Isolated grounding receptacle. Isolated ground receptacle. I want to show you, I have it in my office, guys. The isolated ground receptacle, the yoke, is isolated from a grounding slot. Everybody understand that? The yoke, the frame of the circuit breaker, is completely isolated from the grounding slot. They are isolated by design. Cool? So why would I use something like this? Because I don't want the data to be interrupted, to be corrupted. So the smarter than Chad discovered that the sensitive electronic equipment, cashiers, computer banks, and any places where you use a lot of sensitive electronic equipment, they power them with a standalone, dedicated green wired conductor that goes all the way to the service. We'll talk about this one in a second too. So with this, there's a term that's called isolated ground receptacles. In order to have an isolated grounding system, you have to have an isolated ground receptacle. That comes, guys, by design. And you're going to see in a second how it looks like. Isolated ground receptacle. And you have to terminal to the main, you have to take the grounding conductor to the main service terminal. So you're going to take the grounding conductor all the way to the service. Okay, here's two receptacles. Can you guys look at these two receptacles? One of them is isolated ground, and the other one is not isolated ground receptacle. This is non-isolated ground receptacle. I don't know if you guys can see. I want to emphasize this here, right here. Can you guys see that the box and the frame and everything is tied to the box, the frame, and the receptacle are tied to the same conduit, which is, this is where you're getting the ground. So here's the ground coming into the box, grounding the box and grounding the frame. Grounding the box and grounding the frame. Can I have thumbs up, Chad? We fully understand how through the conduit, we grounded the box. The box is grounded, as well as the frame and the receptacle and the slot, the grounding slot right here. Okay, so that's non-isolated ground receptacle. If you guys look at the isolated ground receptacle, look at the terminal here. The grounding slot here, right here, is actually grounded through an insulated equipment grounding conductor that goes all the way to the building disconnect, the separated drive system, or to the service, So they take a conductor. If this is an isolated ground receptacle, you know what they do? They take a conductor from this slot that grounds only this slot, not the frame, the slot. Take it through this panel. They don't land it here. They take it through this panel, all the way up through that service, and the ground takes that green conductor all the way to the surface. Now this is not how they do it, but this is one way of doing it. Does that make sense where this wire is going? Can I emphasize that if you have an isolated ground receptacle, then Andrew, my friend, then you have to have two grounds. Do you guys understand that you have to have two grounds here? One ground is ground number one. That's the clean ground. Ground number two, I'm going to put it in red here. Ground number two is the one that's going to ground the frame, that frame here, and eventually is going to ground these receptacle, the frame of receptacle. This will be ground number two. Why do I need two grounds? One ground to ground the computer, when I put my computer here and grab my computer and feed it from here and here and here. This is my computer. When I plug it in here, my computer frame now is the frame of the computer is connected to the clean green ground. That's what they call the isolated grounding receptacle, isolated grounding system. Can you have thumbs up, Chad? Where do we use it? For electronic equipment only, where sensitive information is being handled. Cashiers, banks, and so forth. Offices, in our office, guys, the building that you have, we're asking for isolated ground receptacles in the office areas. Any question, guys, about this? Can I emphasize that ground has to go to any of these three, to the building disconnects, to the service, or to the separated drive system? Can I have thumbs up, Chad? We fully understand that one? Okay, so that's basically what two type of ground. Why would I go? Is this code? Does the code even care about this? No. Does the code even care about this? No. Why do we use it? Because we want to minimize the interference. So when they take $10 from my bank account, it doesn't show up as $100, another zero added. Any question, guys, about isolated ground receptacles? Everybody's okay with that one? 2 grounds. I can't emphasize here. How many grounds do we have? 2. Here, ground number 1 only. We only have 1 ground. We only have 1 ground. They use them in the hospitals, guys. 2 grounds are also required in a hospital, but isolated ground receptacles have been eliminated from use in the patient care areas. Patient care areas, you can't use this in the patient care areas. You need 2 grounds, but you can't use an isolated ground receptacle. Any comments, any questions about this? Can you have thumbs up? We fully understand isolated ground receptacle. Okay, cool. Because when you read through the spec that you guys have, it's going to ask you about another ground. Why do you have 2 grounds? 1 isolated ground, 1 dirty ground. Okay, here's what the isolated ground receptacle does for you for living. It eliminates all, well, it actually minimizes all of these voltage sags, spikes, and surges. With isolated ground system, guys, they also have surge protective devices. Do you remember what when Todd was here and he was talking about surge protective devices? And he said you put surge protective devices in the panel that have isolated ground receptacles, so you minimize the sags and the spikes and the surges that comes into the system. So here's your voltage coming really nice, and all of a sudden it went all the way to the Lord, down to the devil, and came back. That's a surge, right? Here's your surge. So you're going to cut these. These are cut not by these are minimized by the grounding electrode, isolated ground, minimized, not eliminated. But then if you have with the isolated grounding receptacle, what they do is they have another electronic device that's called surge protective device. That guy takes this and chunk it, get rid of it. Now remember, not the isolated ground system that does that. In conjunction with it, you use surge protective devices. Okay, statics is gone, eliminate statics. Lightning strike, surges from lightning strike. Electromagnetic interference is a big deal. RFI, radio frequency interference. Improper grounding, because now we have 2 grounds, must be protected from disturbance. So all these, the advantages of having a grounding, isolated grounding system. You're guaranteed that your electronic equipment will not guaranteed, but you do everything you can to make sure that your electronic equipment is not going to burn because of surges, so surge protective devices. And number 2, you're not going to corrupt the data because of interference from other power systems. Any comments, any questions, guys, about that? So everybody understand why electronic equipment grounding is very important. There is a standard in a data center that they ground completely different, guys. Even they use equipment ground conductor number 4 to be tied to the frames of the servers in a data center, and and this is not enforced by the code. It's enforced by the manufacturers of these electronic sensitive equipment. In order for you guys to get the insurance company to get you to license your data centers, they force you to ground it in a certain way and get label that's grounded based on this system. Otherwise, if you don't do it, the inspector wouldn't care, but you wouldn't get this data center insured, the equipment in the data center. So it's a big deal. The only thing I want you guys to understand that it's a big deal. Sensitive electronic equipment is a big deal for grounding them. The only thing you need to, Zach, to understand is pull an isolated grounding conductor number 14 all the way to the service. Number 1, number 2, surge protective devices. That's the only thing, 2 things that you can do. Okay. So grounding, ungrounded conductor, grounding conductor, and neutral must be properly sized, tightly connected, and correctly terminated. These are also a couple of other things to take into consideration. And you have, if you guys go to Article 250.118, it will give you a list of all approved equipment grounding conductor. Equipment grounding conductor. And these equipment grounding conductor, rigid metallic conduit, EMT, intermediate metal conduit, an equipment grounding conductor. All these guys are approved method of equipment grounding conductor. Either a wire, a separate wire, or most of the time, rigid metallic conduits, 99% of the time, are approved as equipment grounding conductor. Metallic, rigid, non-flexible metallic conduits. Non-flexible metallic conduits. Any comments, any questions about taking care of your electronic equipment by properly terminating the hot and the neutral, probably torquing them, probably grounding them, surge protected devices at the panel that feeds them, and probably properly providing an equipment grounding conductor based on 118. Any comments, any questions? Is it Monday or what, guys? Putting you to sleep here? Okay. Moving on into GFCI. GFCI. GFCI this time is for non-residential. Now remember all the residential stuff that we did, Adam? It's in the back of your mind. 2 feet from the sink and 2 feet, all the countertop receptacles in the dwelling have to be GFCI. Now we're moving to non-dwelling. In non-dwelling, the following: 15 and 20 amp receptacles, 120 volt. 120 volt have to be GFCI protected by a receptacle or a circuit breaker. So you can have a receptacle, GFCI, or you can have a circuit breaker, GFCI. Can I have thumbs up, Chad? There are two protection, GFCI receptacle or GFCI GFCI device. Well, where do I need a GFCI in a non-dwelling? Where do I need a GFCI in a non-dwelling? Here's a list. And now remember, you guys are designers. If you see, here's the rule. The rule, if you have a receptacle in close proximity to water, what do? GFCI. That's the common rule. If in doubt, as a designer, what do? Always go GFCI. So remember, electricity, water. Any location where there's a water in close proximity to electricity, you're going to eliminate it. Look at this. First example. So you have 15 and 20 in bathrooms. Anybody knows why in bathrooms, commercial bathrooms, you have to put a receptacle in GFCI? What do we have there? Water. Thank you. In kitchens, anybody knows why in a kitchen, in a commercial kitchen, that you have receptacles, you have to put it in a water, right? Kitchen countertops. Rooftops. On the rooftops, anybody knows why if we put a receptacle outside, you need GFCI? Wind. Thank you. See, can you see the word? Outdoors. Outdoors. And within 6 feet of any sink. Within 6 feet of any sink. Within 6 feet of any sink. These are your location for GFCI receptacles. Any question, guys, about this? Any question about this? Now, here's my question for Kerry, my friend. Suppose that you have a mechanical room. Is it bad to put a receptacle for maintenance in a mechanical room in a GFCI? Is it violation of the code, even though it doesn't say in a mechanical room you need a GFCI? No. Is it safer to put a receptacle in the mechanical room where you have all your mechanical equipment that you're going to work on, indoor mechanical room? Is it safer to put a GFCI receptacle? Yes. So even though it's not saying it's a GFCI required, but it's a good idea to put a GFCI receptacle there. Any question, guys, about the GFCI? These are directly from the code, right? 210.8b. 210.8b, I believe. This is where you got all this information, 210.8b. Any question about receptacles? Any question about receptacles in a GFCI in a non-dwelling? In a non-dwelling. We know where dwelling is. We just finished the dwelling. Okay, so that's 7, 8. Okay, for non-dwelling B. So bathrooms, kitchens, rooftops, and outdoors. Bathrooms, kitchens, and rooftops, and outdoors. So your kitchens, It doesn't say countertop kitchen, does it here? It just says kitchens. So how do we define a kitchen? Remember how the kitchen is defined if you have a permanent lunchroom is not a kitchen. A lunchroom becomes a kitchen if you have a sink and you have a permanent place to prepare food. A permanently installed microwave that constitute a permanent place to cook, right? So you have to have a sink, countertop sink, right? And a range, a permanently installed range or a permanently installed countertop microwave or whatever. So that's how constitute. So some people get confused, guys. You walk into a lunchroom and there is no lunchroom is not a kitchen. But remember, all of us engineers consider the lunchroom as a kitchen. I'll put GFCI receptacle in it, especially the countertop.
It does say stuff before you break areas and you forgot them.
In the code?
No, in the book.
Absolutely. 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 Okay, so that's your receptacles. When you change a receptacle, it talks about changing receptacles. When you change an existing, you guys are not electrician, but if you walk into remodeling, Andrew, my friend, you want to remodel a building and you have a receptacles and non-GFCI in a kitchen, in a commercial kitchen, so you have to change them with what? GFCI. This is typical, guys. You have to change a receptacle that's non-GFCI with GFCI receptacle. This talks about electric baseboard heaters. You guys remember when we talked last quarter about electrical baseboard heaters, fixed electrical space heating equipment, Article 424. We sized a couple of things about this last quarter. Receptacle, your receptacle can count. If you put a receptacle in that baseboard heater, it will count as one receptacle based on your need. And one thing shall not, can you guys see that? Shall not be fed from the circuit that feed the heater. I know we talked about this one before. So if you have a heater, a baseboard heater in a commercial building or residential, you have a circuit that feed the heater and another circuit that enter the frame of the heater to feed just the receptacle. Any question, guys, about this one? So you can't have in a commercial building a baseboard heater for certain areas that comes with a receptacle, built-in receptacle. You bring two circuits to it. One circuit to feed the heater and one circuit to feed what? The receptacle. Can I have a check for that one? Everybody's okay with this? These are all ideas, guys. Okay, so that's all for receptacles. We'll talk about different type of receptacles in a second. Switches. Switches, you're looking at the term snap switch right here. This is called snap switch. We talked about this one in the MEC code, called them annual snap switches. A lot of people call them toggle switches. There are two types of these boys. The type that can handle the AC only and the type that can handle the AC, the DC, general use snap switches. AC, DC. We're looking at the AC here, but if you are to break DC, anybody knows why the DC is an issue when you break DC? We don't have a lot of DC, but with photovoltaic system coming, because when you break DC, the arc of a DC is more dangerous than arc of an AC because there's no impedance. The only impedance is the resistance. There's no XL. So anyway, so remember, when you break a DC circuit, it's more dangerous, more arc comes out of breaking a DC circuit than out of breaking an AC circuit. Just remember this one. So your equipment the switch have to be able to break a circuit that's fit from an AC, so it has to be rated for that one. Okay, grounding switch and metal faceplate. This talks about grounding it, guys. The receptacle that you're looking at, these are not the frame of the receptacle. The frame of the receptacle, so it had to be grounded as of 1999, I believe they start grounding it. The box have to be grounded, and the cover, if it's non-metallic, doesn't have to, but if it's metallic, the screws right here that goes right through the cover will ground the cover. So three things you need to ground for the receptacle. The box, the house of receptacle have to be grounded. The frame of the receptacle, am I saying receptacle? The box of the switch have to be grounded. The frame of the switch have to be grounded. Same thing for receptacle, by the way. And the cover, if it's metallic, have to be grounded. Can I have thumbs up, Chad? And all these are done by the schools and so forth. So you can ground the box if you can tie it to MC cable, AC cable. Guys have different ways of grounding, approved methods of grounding. The yoke has to be grounded. The nameplate, the faceplate, or the faceplate have to be grounded too. So all these, the metal box have to be grounded. All these together have to be grounded. Cool? Thumbs up. So what most of the time, if it's non-isolated ground receptacle, is they bring a conduit to a box, like you're looking at it right here. So now this box is grounded. Can you see that? And they pigtail the grounding bar into the box, tied to the box. So now the receptacle is grounded, the cover is grounded, and the box is grounded through the EMT conduit. Cool. So that's the grounding for all these. I know we're not electricians, but it's good idea to do that. Color coding for conductors. This is really cool. Color coding for conductors, ungrounded conductors. So ungrounded conductors. The code says, guys, about color coding for conductors. I have in your, actually, why don't you guys go, I want you to highlight this, please. If you go, because I thought these are one of the most important things that talks about color coding conductors. In page, can you guys go page 102, please? In your book, 102. And in the left-hand side of 102, they give you the industry standard color coding. In page 102, the industry standard color coding for your system. So we have single phase, 2-wire, black, white, 120, 240 single phase in a conduit, 3-wire, that will be black, white, and red, 28, 123 phase, 4-wire, black, white, red, blue. Everybody can see that? This is page 102 in the left-hand side. If it's 240, 3-phase, 3-wire, corner grounded, that will be B phase. The grounded conductor will be B phase, black, white is the B phase, and red. 122, 43 phase, 4-wire, high leg, so you can give you the configuration. And 480, 277, that will give you the brown, gray, orange, yellow, and 483 phase, brown, orange, yellow. Can you guys highlight this? If you're a designer, these are very, very important. I'm going to summarize two of them. Two of them is 28, 120, so you're going to have red, right? Red, black, you start with a black, red, blue, and what? And white. That's your 480, 277. 28, 120. 480, 277, you're going to have the brown, the orange, and the yellow, plus the gray as a grounded conductor. The code talks about ungrounded conductor, the phases. The phases, guys, cannot be white, cannot be gray, cannot be any continuous whites. These are the what cannot be. Green must have an outer finish. Ungrounded conductor must have an outer finish that is other. That's other than these. So that's all what they talk about the phases. So please don't make them gray. Please don't make them white. Please don't make them green. Make them any color. Can I have a pink as phase A? No problem. So the industry have in this page 102, guys, that's standardized industry standard for different type of system. Can I have thumbs up, Chad? We fully understand what's on page 102 for conduit. On the right-hand side for cables, almost the same thing for cables, NM, ACMC cable. If you look, guys, a 3-wire cable, we have white, red, bare, or green equipment ground conductor. 4-wire cable, you have to have a black, white, red, blue, bare. 5-conductor cable, you can have a white, red, blue, yellow, bare, or green equipment. You can have cables almost in any color you want, but typically they match the system. So you can have a system for 288, 120, a system for 8277. So that's the most popular colors are black and white and red and blue and yellow. These are what we just talked about, guys. The system, the voltage system for phase conductor. Ungrounded conductor. If you have ungrounded conductor, number one, are generally available in black. This is not true anymore. They have color coding, guys. Number one and larger. They used to make them all black. Now you can have different colors, any color you want. Any comments, any questions about the color code for the phases? Color code for the phases. Phase color code. Phase color code. The grounded conductor, the only thing you have to remember about the grounded conductor is you have to have the outer finish of either continuous white or gray color, or have an outer finish that has a 3 continuous white stripes. So typically white or gray, that will give you the grounded conductor, the neutral. Can I have thumbs up, Chad? We understand that one? Okay, cool. So that's equipment grounding conductor. Either you have, and we talked about this one before, you have a green or a green with yellow stripes. That's your typical, or I can have bare conductor. I can have bare conductor. So equipment grounding conductor. So color coding is not mandatory. Okay, so that's basically the typical wiring methods that you can use. Any comments, any questions, guys, about the wiring methods? Recap. We have a 208/120 system, just our system, 208/120 volt, 3-phase. That's the system that you guys are dealing with. For a system like this, you're going to have, what are we going to have? We're going to have a black, right? We're going to have red and blue and white. This is and green, green. This is a system at 3-phase. You're going to have a black conductor, a red conductor, a blue conductor, and a white conductor plus the green. These are your 5 conductors for a 3-phase system. Can I have a thumbs up, Chad? We fully understand that one? Okay. If they're number 6 or smaller, they have to be color coded like this. If they're larger than number 6, you can actually take one conductor, one color conductor, and put a tape on it. So if you walk into a building, guys, and 4-aught each, you're going to find all these conductors, the 5 conductors here, 4-aught, therein, all these 5 conductors, 4-aught, you're going to find them all black, all of them black, right? If it's 4-aught. But with the black, they come at the end, wherever you terminate them, and you put a label, a tape on it. So you're going to tape each one of them to identify black. It's black is already black. The other black, you can put red tape on it. The third one is going to be blue tape. The fourth one, you're going to put a white tape on it. And the fifth one, the ground, what do you think you're going to put on the ground? A green tape. That's how they do them if they are larger than number 6. Any comments, any questions? Any comments, any questions about identifying them? So that's basically what this is. This is color coding. You guys know, not electricians, but a gray in the past, which has been used as a hot, as ungrounding conductor. We actually have in one of our buildings, the gray is used as ungrounding conductor. If you have 2 systems in a building, this is very important, Joe, my friend. If you have 2 systems in the building, you have to have color coding for the 2 systems. So if you have a 2 system, 480, 277, 120, 208, you have to have one color code for the phases, and one color code is for the ground of this system, and another color code for the phases and the ground of the other system. So that's where they typically use a white with the 208, and where's my gray? And gray for the 480 here, and the 208 here. Volt and volt. Any comments, any questions, guys? Any comments, any questions? So important, guys. I know you're an electrician. So important, electrical designers, to know, at least understand these terminology that they use. When you're using cables, we looked at the color codes. They typically use the same color coding that we use in conduit for the most part. But if you have conduit, you have a lot of, you can pull as any color code that you want. But if you're a cable, you're limited to what the manufacturers of this cable use. The manufacturers of cable are limited to 2 things, Jeff, as you and I know. They have to give you a grounding conductor, which is bare or green. They have to give you a grounded conductor, which is white or gray. And then the other colors are whatever they want them to do. And typically they use, like we said, they use the black, red, blue, and they use the brown, orange, yellow for different systems. And you can have other colors too. So be aware of that. Black color, insulated conductors. Okay, when this is a couple of wiring methods, guys, that you use. The first one is with a cable. You can see the black. Look at this schematic for this. I have the black. I break the black. If you guys don't know how to wire, this is a very important thing. So you bring the circuit into the switch. So the switch has a neutral, and you switch the hot, right? Like you see here. And based on 2011, you have to have a neutral at the switch, right? You got the switch, and no problem. So that will take care of your system here. That will take care of your system. If you bring the service, if you bring the circuit at the light, then you have to re-identify the neutral. Then you have to re-identify the neutral. In the case that re-identifying the neutral becomes almost obsolete in certain applications. Anybody knows why re-identifying the neutral becomes obsolete in certain cases? Because based on 2011, you have to provide a neutral at every switch, So for example, right here, we used to re-identify the white as a black, bring the power into the switch, out of the switch with the other black, with the black. Here, I have to bring the neutral directly to the switch. Any question, guys, about switches? Switches, as of 2011, you have to provide the following for every switch. You have to ground every switch, equipment ground conductor, and you have to provide a neutral right at every switch that switches lights. Any comments, any questions, guys, about the color coding in cables and conduits? You can get switches, guys, in the following formation. You have single pole, three-way, four-way, and double pole switches. We talked about this one before. Occupancy sensors, that's a new topic for you. Occupancy sensor is an electronic device that sends motion and trigger little contact to open or close based on the setting and turn a light on and off. Cool? That's what you guys are going to be doing with us. Occupancy sensor, so it acts as a switch. We'll look at this, a couple of them in a second. Receptacle cover, raised cover, and faceplate covers. These are just for grounding them. We talked about grounding the yoke and the boxes. Wet location. Okay, if you have receptacles in a wet location, if you have moving into receptacles and switches in wet location, you have to have in use. If you have receptacle in wet location, you have to use the following. You have to have in use cover. See that bubble where you plug in and it covers it? In use cover. And the receptacle have to be weatherproof receptacle. Weatherproof receptacle, and we have to use an attachment plug cab that is inserted into receptacle when no attachment plug cab is inserted into receptacle. So you have to have the bubble cover. Any question, guys, about receptacles in wet location? In use cover, weatherproof. In use cover, weatherproof. Important. This is just, and then the rest of them, guys, it goes through the definition of a damp location and dry location, because the NEC code book says if you put it in a damp or wet location, you have to have a weatherproof receptacle. If you put it in a wet location, you have to have weatherproof receptacle and an in-use cover. So this is where the damp is, protected from weather and not subject to saturation. So the whole idea is no saturation. With water or other liquids that's subject to moderate degree, but it's subject to moderate degree of moisture. So they have moisture, but protected from the weather and no saturation of water, right? Canopies, porches is a good example of that. Under the canopies and the porches. Dry location, no dampness and no wet location. No dampness and no wet. That's your dry location right here where we're standing. Wet location. Anything underground is considered wet location. You can know why. Anything in concrete slab, direct contact with underground is also wet location. Any location with saturation of water, like car washing machines, is considered wet location. Who cares? Who cares? 1 second. Who cares? Because if you have a receptacle in wet or damp location, that receptacle have to be weatherproof. That receptacle will run you a couple of dollars. Weatherproof receptacle. Yes, sir.
Does underground then just mean anything below ground level, or does
Under indirect contact, underground is under the dirt, basically. Yeah. Yep. Okay. Any comments, guys? Any questions? So that's basically what that is. I want to show you a couple of things. Let me give you a quick break and I'll show you a couple of pictures. How about take a quick break? It's Monday. Let's take a 5 minutes break. Allow me to go over, if you graduate from Dunwoody without knowing this configuration, ask your friend Chad for refund. You know, really is. If you don't know that the bottom, that thing is a ground, and this is a white, which is the grounded conductor, and this is the hot, you really should ask me for a refund. I'm not kidding you. Cool? Thumbs up, Chad. We fully understand. If you want to remember the smallest slot is hot for safety, right? Just remember, there's hot here. If we touch this, you get electrocuted. That's the only location where if you touch, you get electrocuted, right here. If you touch any of these, not like you want to. If you touch this one, you're gonna get electrocuted. Any other ones, you don't get electrocuted. Cool? So that's my hot, my hot. Cool? If you don't know that one, ask Chad for a refund. Okay, the only difference between these two guys, NEMA configuration, as you know, as oops, where did I go, Chad? I went too far. Too far. Okay, the only difference, this one is 15 amp, and this one, can you guys see? Where is the other one? I go too fast here. Okay, here's a 20 amp. That's the only difference. It's 20 amp, right? So this, when you go to commercial building, we use a lot of these stuff. This is a configuration for a 20 amp 120 volt receptacle. Just remember that little thing. If you don't have this little horizontal slot, it's a 15 amp. Can I have thumbs up, Chad? Because these are the most convenient receptacles, 20 and 15 amp. Cool? Okay, so that's a 15 amp. This guy is a 15 amp, as you can see. So this boy is going to be 15 amp, and the other one is a 20 amp. Okay, so these are cool. Everybody's okay with that. 15 and 20 amp. Okay, so here's these are some of them are 120. I think this is two. Which one is that? This is the one on the right is, now I have to look at that one. The one on the right is 240, I believe. 240, 120, 15 amp, and is 20 amp only, B is 30. And you don't have to, thanks God, we don't have to memorize that one because you have NEMA. It will get you, which page are we NEMA pages? Got me by NEMA configuration. Okay, so that's NEMA, the first NEMA. Okay, that's 2.1 with this one will be 120 20 amps, the one on the B, and 15 amp, and the other one is 15 amp, 20 amp, 120, and the other one is 30 amps, 240. This one, the A is 30 amps, 240. Okay, so without knowing all this, we'll take you guys into the configuration. We talked about this one. I'm going to go directly into, oh, here's a really nice picture. I want to remind you guys, when you have an isolated ground receptacle, can you guys see the ground here? Can you just follow with me? See that ground slot here? It goes through the pipe, and it passes through this panel, all the way it terminates. Where does it terminate? In the service. That's how they do them. Now, obviously, that's very expensive. This is a very expensive way of doing it. But you know how they do it in real life? They have an isolated ground here. They have an isolated ground right in here. And then this conductor will land in here. And then you take a feeder all the way up to here. And then all the receptacles, isolated ground receptacle, will be landing on this one, right? Does it make sense? So they have an isolated ground in that panel where all the isolated ground wires will land on it, and then they group them all together and take them to the panel. That's what typically we do. Otherwise, every branch circuit that goes from here is going to go all the way down to the service. That would be a lot of wires. Can I get you guys to understand how they do them? They have two grounds in the panel, one dirty, one clean in one panel. Typically, one clean, one dirty. This is isolated here, and they group all these conductors right into this panel. Thumbs up, Chad? Yes? We understand? Okay. So that's how isolated ground receptacle works. This is just a really nice picture of a three-phase system. When we talk about three-phase system, can you guys see how when you take an RMS value of an AC system, I don't know if you guys can see that, this becomes like this. Does that look, does it look at this here, the top? Does it let this top, doesn't this look like a DC? This is the reason why AC three-phase is superior to AC single-phase, because your equipment is going to look, it's going to see that little almost DC, right? Almost DC. So your equipment, unlike this, here's how this signal is going to go up and down, right? But because three phase, when one is up, the other will be down. When one is down, the other will be up. So your equipment constantly seems similar to a DC circuit. Who cares? It makes your motor run smoother, more efficient, better. But that's the key point is for a superiority of an AC system. That's what I would just want to mention here. Here's the spikes that could go and burn your equipment. I thought that's really nice picture of. These are the ones that kill your computers. All these different reasons. See that? Chad was talking about all these spikes. These, if you have a motor, they don't affect motors that much, but they affect computers and electronic equipment a lot. They burn them. Surges, they call them surges. That's why your equipment at home are plugged into surge protector device to get rid of all these. Shunt them, cut them off, zip them to the ground, tie them to the ground. Can I have thumbs up, Chad? Okay, cool. So having an isolated ground receptacle will minimize this. Will minimize this. Here's how you wire in a three-phase system. I can't emphasize, please, if you haven't did branch circuit, please pay attention to this, please. This is how we typically wire in a three-phase system because you guys haven't done a three-phase, right? So you take a three-phase circuit here, basically, right? There is no multi-wire branch circuit. Can you guys see that? And we're feeding multiple receptacles. Later on with Chad, you're going to see we're going to feed 6 receptacles here. So I have 6, 6, 6, 6, 6, 6. Now I can feed more than that. Typically, if it's an office cubicles, you don't want to be feeding more than 6 of them in one circuit. So how many can I feed in an office environment? 1, 2, 3, 4, 5, 6. 6 times 6 is 36 receptacles. It fit from a 20 amp, 208/120 volt system. Can I get you guys to understand that one? That's how we wire receptacles. Now we're pulling a neutral. We're pulling a neutral with every phase. That's what we're going to be asking you to do in office building. Because of harmonics, we like to pull a neutral with every phase. Jeff and then you guys talked about this one. That's a typical installation where you pull a neutral with every phase. Can I have thumbs up, Chad? Cool. Take the top one. The top one, I have another 20 amp circuit tied together. I have, this is 3-phase, right? Everybody, this is 3-phase. And I'm pulling a neutral with every circuit. And I can put, based on the size of these fixtures, I can go my range based on the size of the light. I can put probably 20 lights, 20, 20, 20, 20, 20. 1, 2, 3, 4, 5, 6. 6 times 20 is what? 120, right? 120 fixture on a 20 amp circuit with 6 conductors. Is that cool or what? This is branch circuit. That's exactly what you're going to do. For the building that we're going to have, you're going to circuit with 3-phase. Circuiting with 3-phase, you'll always have to group them together. And you can, I'm throwing these numbers, you actually can go higher than that, depending on how many fixtures you have. We have a calculation that we're going to use for this project. Any question, guys, about this? Now, this is pulling one neutral, neutral with every one of them. Now, what happens if I pull one neutral shared between all these circuits? That's called multi-wire branch circuit. One neutral that's shared between all these circuits. Can I do that? Yes. A lot of engineers, guys, because of harmonic, they want you to pull one neutral. But unless the engineer tell you to pull one neutral, what do? Multi-wire branch circuit. So instead of having how many wires here? We have 6 wires here and 6 wires here, right? I can, not including the equipment ground conductor, I can pull, instead of 6, I can pull 4 wires. 4-wire system, 4 wires. Right? If I put a multi-wire branch circuit. Can I have thumbs up, Chad? We understand how this goes. So how am I going to do it in this project? Unless they tell you to pull an isolated grounding, a grounding conductor with every circuit, we're going to use a multi-wire branch circuit. Typically in the office, we pulled a neutral with every circuit. They're telling us to pull a neutral with every circuit. Okay, this is one of the most important wires that you guys are going to see. It really is. This talks about the GFCI work. You guys have seen this many, many times. So GFCI work, it senses the difference. If your difference is 6 what is it, 6 milliamps. If you have a 6 milliamps difference right here, 6 milliamps, 4 to 6 milliamps, it will see the difference that's going through somebody's heart, and it triggers, this will sense a signal over and open the contacts, right? Everybody knows how the GFCI works. There's a sensor. It senses the current in and the current out. If they're not within 6 milliamps, less than 4 milliamps of each other, they will trip. This means there's a few current that's leaking through somebody's heart. Thumbs up, Chad? We understand that? Okay, so this is the baseboard heater that we talked about, just very quick. We talked about it in the residential too, and we said in a case like this, you're going to have a 20 amp circuit coming here, feeding this, and you're going to have another, say, 20 amp circuit here, feeding the equivalent. So two separate circuits feeding, one for the baseboard heater, one for the receptacle. Thumbs up, Chad? Cool. Okay, so that's talked about. Okay, this is my favorite. When you deal with systems, if you guys are good designers, you have to understand these systems. Okay, there are 3 types of power system you're going to encounter. One is grounded system, ungrounded system, and impedance grounded system. I'm going to save you the hassle of talking about 2 of them. One is impedance grounded and ungrounded. We're not going to talk about these. 90% of your time, 90% of the time, you're dealing with a grounded system. A grounded system. Cool? The grounded system, guys, 90% of the time, you're dealing with this grounded system. Right? That's your 90% of the time. This grounded system. This is Y grounded, center Y grounded, right? From this system, you're going to get your 208/120 volt, 3-phase, of course, and you get from this system 480/277 volt, 3-phase. In a commercial industrial, this system will cover 90% of what you're going to be seeing. Okay, they call this system is called, guys, 4-wire system. 3-phase, grounded 4-wire system. So this is a 4-wire. Anybody knows what 4-wire? Can you count the wire? 1, 2, 3, 4. 4-wire. Why 4-wire? 3-phase and a neutral. The ground, everything need a ground. The ground doesn't count. Can I have a thumbs up that if you don't understand this system, you will never be a designer. Really, guess your designing career, goodbye. That's a system that's going to create, you're going to start every building with a system like this. This is a generator or a transformer. Typically a transformer outside the building that's Y grounded, 4 wires, 3-phase and a neutral coming to your building, and from there you feed the whole building with either 28120, which is the one that we are using, this one, or 480/277. Can I have thumbs up, Chad? We understand that? Okay, that's 90% of your life is going to be there. The other 10%, Jeff, in a commercial, you will encounter these 2 ugly ones. This one and this one. This one is called corner grounded delta. This is a corner grounded delta. They take 1 phase and they ground it. Why would they do something like this? If you have a delta, is ungrounded. There's no ground in a delta. To stabilize the voltage, guys, in a delta, they take 1 phase sometimes and they ground it. Because ungrounded system creates spikes in your system, so it creates troubles for you. To eliminate the trouble that's coming out of delta, the smarter than Chad said, what if we take 1 phase and ground it? It becomes corner grounded delta. This is called 3-wire system. 3-wire system. You're only going to deal with this one how many times? 10% of the time. Typically not used. Typically after fact. Typically to solve a problem. 10% of the time. Same thing with this one. This one also used 10% of the time. This is if you need the voltage that you can come from this is 240/120 3-phase. If you want a 120 3-phase, not single phase, that's the only way you can get that. This is also the same thing, a 4-wire system. What would we use a system like this, guys? Only 10% of the time. You would never ask for this. A place where you have a lot of 3-phase loads and a very tiny single-phase load. Lift stations, they use system like this. Well houses, they use system like this. Where the motors are running at 240 and the lights and the receptacles are running at 120. Can you have thumbs up, Chad? We understand this system. So the most important one is the one that I highlighted here. So these are the three-phase. These are, I've never seen this used. I don't know what the application of it. This is your residential, right? Residential single phase, 240/120 volt. Okay, we exceeded that one. Can I emphasize, if these are the systems that you start, you always start a power system with a transformer. So this one, the one that we highlighted right in here, is the one that you're going to see 90% of the time. Oh, the other side. Oh, good point. This is the secondary side of a transformer. Very good point. What's a primary? That's what comes to your building. Let me erase this one. I'll show you on the most important. So any question about this? We understand that? Cool. Now let me go, and since talk about very quick here.
Those top ones we only use for the really small voltages.
The top one is dwelling. Very, that one? That's residential.
Well, the other one.
That one?
The only time I've seen us using it is when we were using it for like the computer voltage or small voltage.
Yeah, I've never seen a service 120 though. 120 only. This is 120 only. Anybody? Darren? 120 only, no 240. I'm sure there's an application. I've never seen it.
What do they use for like 24-volt control systems or something like
Yeah, maybe, yeah. But we're talking about service coming into the building with only 120. No 240, 120. Okay, let me talk about what my friend asked. Here's the secondary. So these are your phases. Here's phase A, and here's phase B, and here's phase C, and here's my neutral. Right? I'm going to pull my neutral, right? Here's my neutral. Okay, now this is the secondary of the transformer. The primary, typically the primary will look something like this, delta, the primary, and this will be phase A, phase B, phase C, and this is under the control of the electrical utilities. That's how your transformer is going to look like. The primary, that's what we're going to do tomorrow, by the way. Tomorrow. The primary is ABC, and this is typically 13A, 13,800 kilovolt, 13,800 volt, or 13.8 kilovolt. This typically 480/277 volt, of course 3-phase, and this one 208/120 volt, 3-phase. Can you guys see the primary and the secondary of the transformer? Can you have a thumbs up? We fully understand that, Chad. Andrew, my friend. Cool. Tomorrow, we're going to be doing calculation on this transformer, the most common source of power to any building. Cool. How to size the primary and secondary of this transformer. Aaron, does it make sense? So this side is the utility side.
The Y is going to drop the voltage down when you transfer from the delta to the Y. But is it still 480 instead of the 240, 120?
Well, you have to decide. Do you want a transformer that gets you 480 service, or do you want a transformer that gets you 208 service? This is a decision that you make. Cool? Yep.
So we went through a lot of that in motors.
Yep, absolutely. Based on the load and based on a couple of factors. Any question guys about this? This is, can I put 90% of the time you're dealing with a system like this? Either 28, 120, or 240. Our project carrier, my friend, is 28, 120. This project, next project is going to be 480, 277. Okay, so that's your project. So let's go directly. So we talked about the system. Okay, there you go. So that's my system that we talk about. Let's go back into, we talked about this wiring. Please, guys, please, I can't emphasize, in 2011, you need a neutral right in here. You need a neutral right with every switch. Here's a three-way switches, the travelers. Everybody knows what the three-way switch is, how you tie the travelers together. The traveler is tied to the traveler. And you guys, here's a wiring. Please go ahead and guys do the wiring method. Here's a wiring method where you bring the service into the switch circuit, and here's where you bring it with a cable. Can you guys see when you bring it with a cable, you need a neutral. you need a neutral. This is great for estimators. If you don't know, if you're using an MC cable and you don't know now that if these receptacles are for light, you have to bring another wire for based on 2011. Your cables are going to be sized differently, right? Because now all of a sudden you have a four conductor cable here, 1, 2, 3, 4, right? With the ground.
No more dead end freeways.
There's still some application, but not a whole lot though. Not a whole lot. Not a whole lot. Here's how a three-way and four-way switch guys work. Everybody's familiar with that? Three-way and four-way switches. Please go ahead and review them. Please review these wiring methods. This is just great ways of, I know we do a lot of wiring with you guys. A four-way switch, the most important thing for a four-way switch is the travelers. Travelers really is. Travelers between the four and the three-way switches, and then the switch return and the supply and the return of the switch. And any question guys about this one? Any question? I can't emphasize if you're using cables, you have to have a neutral with every switch now. We have to have a neutral with every switch. Only if you're using cable. If you're using conduits, you don't have to. Only with cables. Any question about these wiring guys? Does it make sense? Aaron, if you want, we can take this and we go wire in the lab. I assume everybody else is cool. When it comes to taking off, Adam, and we do three-way switches, and you're going to come here and you're going to take off this as this will be a three-conductor cable, right? Between the two of them, three-conductor cable. Of course, with a ground. Not a two-conductor cable. So that's where wiring becomes a big deal when you do the takeoff. Not like you guys are going to go wire. I hope you can wire.
So what's the theory behind the neutral only the cable?
Because if you change this one to occupancy sensor.
Because you can always pull in a neutral.
Oh, yeah, for conduits, yeah. Because, why not in conduits? In conduits, you don't have to provide a neutral. It's already here in this case. Because in conduits, if you need a neutral, what do? You pull, hopefully, you have enough room that you can pull a neutral. In a cable, hard to pull a neutral after the cable is there. It's not impossible, but you have to rewire the system. Any question guys about three and four-way switches? So these are, I assume by this time is everybody's okay. Okay, this is two-pole switches. You use them in a two-way system. So suppose that I have, I don't know, these are switches. You will switch two circuits. This is a circuit is 208. Suppose you have a 208 voltage. You brought circuit to multiple lights, and then to switch the two circuits together, you need a two-pole. Now, Andrew, mistake number one when you start circuiting and putting switches. I've seen it over and over and over. The students come and they say, well, this switch is going to switch two circuits. Yeah. This switch cannot switch two circuits. Can switch only one circuit. To switch two circuits from a switch like this, what do you need to do? You are looking at it right there. Two-pole snap switch. Not commonly used. Right? So you need a switch that looks like this. So be very careful when you align your switches with your circuits. The best practice is every circuit assign one switch or more than one switch for every circuit. If you put two circuits in one switch, you are dealing with two pole. Can I have thumbs up, Chad? We understand that one? Okay. Here's all the rest of them, guys. Please review them. Really nice pictures of single different type of switches and receptacles, 50 in a single pole. And this is a 30 amp. I can't emphasize. Here's your 6-30 NEMA 250, 30 amp 250 receptacle. That's typical to what? Range or something. Here's your hospital grade receptacle. It's always identified typically with a green dot like this. That's a hospital grade receptacle. Means it's robust, really good receptacle to use. Can you guys see that? The little identification of that boy. This is isolated ground receptacle. How do you know it's isolated ground receptacle? Because it's orange face. Typically you have to have an orange triangle. Do I have an orange triangle right here? See that one in the center here? This is an orange triangle. The orange indicates it's isolated receptacle. The green in the orange indicates hospital grade. Typically you see these one in hospital other than patient care areas, because you can't put them anymore in patient care areas. Okay, so that's what your receptacles. Different decorative receptacles that you can use. Switches, big type switches. Here's the occupancy sensor. That's why that's a whole change, Jeff and Darren and Zach, my friend, of bringing a neutral to the switch, because of that little occupancy sensor need a little milliamps to work on. In the past, they used to tie it to the ground, because you can get little current on the ground, but the ground is not supposed to be used as a grounding conductor, right? It's supposed to be used only to carry, the grounding conductor shall not carry continuous current unless only under fault condition. So anyway, they change it so you can tie the neutral to it. This is the in-use cover that you have to use. All your receptacles have to have an in-use cover, so when you plug it in and it's raining and snowing, it doesn't affect the plug, right? In-use cover.
That's not really an in-use cover. That's just a weatherproof cover. The in-use cover has.
You have to completely engulf it. You're absolutely right. This is a weatherproof that then it has to have a bulb on it. Yeah, where the plug-in. This will be, you're absolutely right. This is only in damp location. Wet location, I don't know if we have a picture of it. In a wet location, yeah, in the wet, you guys, it's going to be bubbled a little bit where you can plug in. You're absolutely right. So this, you can't use this one in wet location. It has to be used in damp location. Okay, here's a in-use cover. Thank you. That's an in-use cover where you can see that bubble there. We can plug in and at the same time completely plug in the receptacle and completely engulfed and protected. Okay, here's where I want you guys, I want to go over this. This is the NEMA configuration for non-locking. Can you guys see the non-locking? This one you're locking, these are locking type receptacle. You plug them in and lock them. These are non-locking. So if you ever confused by, here's NEMA 115P is a plug, NEMA 115R is a receptacle, no ground with this, guys. Here's the voltage here, here's the amp here. Can you guys see that? A 20 amp receptacle, the typical, the one that we use all the time, guys, are right here. Here's a 15, I'm gonna just, oh, can't get it up to here. There you go. Here's a typical, here's a 15 amp, 120, and grounded conductor. So 5-15R, 515P is a plug, 5-20R, 5-20P is a plug that goes with the receptacle. Can I have thumbs up? We fully understand these NEMA configuration. The plug has to match the receptacle, and you can fully understand why. Because plugging a load that's rated for 240 in a 120 receptacle, you just have burned that baby. Okay, and you can see all the way they still have some future expansion, guys, but up to 50 amp, you can get 50 amp. Here's 50 amp receptacles. Look at the voltage, 277, 240, 250, with a ground right here. So these are all your plugs and receptacles. Oops, did I go to... so these are non-locking type receptacles. Any question, guys, about the non-locking type receptacles? Different, look at the wires here. This 3-pole 3-wire. This is 3-pole 4-wire, 4-wire with a ground, without the ground. See here, 2-pole 2-wire, no ground. Here's 2-pole 3-wire, grounding. So you have to have a ground here, no ground here. 3-pole 3-wire, no ground here. Almost all of them now with a ground, guys. 3-pole 4-wire with a ground. Almost everything have to ground. Cool. Yes, sir.
Why does it say reserved for future consideration instead of just saying not currently used? Are they actually planning on using it?
You never know. Yeah, reserved for future consideration. Absolutely. So if we have a need, we have another NEMA that you can install here. Absolutely. So can you guys see that how it goes? The 15 and the 20. The 20 is for the R for receptacle, 20 for the amps, and the 18 right in front of it is a NEMA number that they assign to it. Okay, let me go to the locking. These are my favorite, the locking one, 60 amp. Look at that. I need a 60 amp receptacle, and I need this receptacle to be 4-pole 480. I don't have it. How about 4-pole 5-wire grounding? Here's my receptacle. Can you guys see that? L2160P is the plug, L2160R. This is 480. Is that 480? Huh? It's no, this is 280. This is use 480. 480 277 right in here. This is 660 L2260R is a 480 277 receptacle with a ground and neutral. Can you guys see phase A, phase B, phase C, ground, and neutral for the receptacle and for the plug? Now, some of you looking here said, are you kidding me, Chad? Where the hell would we use something like this? You'll be surprised. That's how they use, guys, in portable generators when they go to plug a portable generator into a lift station because you lost power into that section of Bloomington. And if you don't move that sludge, the street will be flooded with sewer system, right? Is that a problem, right? So you take a portable generator right next to this lift station, plug it into it, and lock it. These are locking type receptacles. 60 amp 48277 is one example where you can use it for a portable generator all the time. As a matter of fact, we installed 200 amps. Hubble makes bigger receptacles that they use 200 and 100 amp at 48277. Okay, but specially designed. But that's the NEMA configuration. Any question, guys? Any question about that? Does that make sense? Yes, no? Okay, so now remember, L in front of it means locking time. See how it's circular instead, so you lock it. Locking time. The rest of them, guys, do me a favor and do yourself a favor. These are from the examples, the homework. So you're supposed, guys, to walk in there and wire these. You're supposed to wire these lights and receptacles. I'm going to do one of them, and I will let you guys go from here. So if I want to bring the circuit, here's my power. My hot is here. And I bring my neutral. Here's my neutral. I'm bringing my neutral right here. Terminate my neutral in here. Come right here, right? And terminate my neutral in here. And I'm going to go, oops. I want to go all the way to here and put my neutral right here, right? This is my neutral. I'm doing wiring for this boy. So I brought my neutral here and here. Now, Jeff, why did I bring my neutral to the switch? Based on 2011, if you're wiring with a cable, the neutral have to go all the way to the switch. So I brought my neutral. I'm bringing my circuit into this switch. This just terminate here to the line to the switch. Any question about the neutral?
It's just being terminated to the faceplate.
No, just what's a wire nut? Yeah, it's capped with a wire nut. Okay, so now let's take the hot. Now the travelers. The travelers are easy. You have to have a switch coming. Typically, you're going to bring your switch, just terminate here in that, and take it up and bring it to here. And the second one is going to go all the way, because this is a cable. Remember, you're going to terminate it here. It's not going to do anything. And sitting here. These are just capped inside the box. They're capped. Does that make sense? It's just capped. They're not touching anything. Okay? And the last one, my friend, is you're going to take this wire from here and you're going to bring it to this side. I have wired a light to turn on and off with a three-way switch. If you don't know how to do this, ask your friend Chad to help you or ask me for refund. No question asked. You guys are not electricians, but if you don't know how to do that, you will never be able to estimate the system. Why? Take this. Now, what cable, AC cable do I need here? 1, 2, 3, 4. This will be, let's just say, number 12, 4 MC cable. Right? Why 12, 4? Because I need two travelers, one neutral and one return to the one switch top. How many wires do I need here? I need number 12, 3 MC cable. Why do I use MC cable? We're commercial now. NM cable out the window, right? How many wires do I need here? I need number 12, 2 MC cable. Now, when they say 12, 2, they don't count the ground. Everybody understand the ground comes with it, right? So typically, there will be one conductor with the ground if it's an MC cable. Is this important to know how to wire this? I know you guys know how to do it, but everybody else, if you want to be an estimator, you got to be able to figure that out. Okay? Why did I bring the red here? Even though they're not doing anything, they're getting into the box. You know, physically, mechanically, you can't just take these two red wires and run them straight into the receptacle, because you terminate cables and conductors in a box. You can't just terminate them up in the air. Okay? Any question, guys? But the terminals that you land on, here's the terminals. I'm going to highlight the terminals. These are comes. Here's a terminal here, a terminal here. These are terminals. Here's the terminal of the devices. Here's your terminals. Can you guys see that? The rest are wire nuts. Everything else is wire nut. Cool? So do me a favor and do yourself a favor. This is part of your homework. Please do them. Sketch them and show them on your book. I don't want you to guys to draft them. Go ahead and draft them if you want to, but at least sketch them. Sketch them and bring it to your friend's Chad's attention. So as part of your homework.
You don't wire nut for the two red spots in the wire?
This is a wire nut and this is a wire nut, but these are terminal though. A terminal is a log where you land the conductor right underneath it.
A wire nut, you're just tying.
A wire, yeah. There's two conductors with a wire nut. Twist them. Make sense? Okay. Inside the box, there's a box here. It have to be a box. They just connect them with a wire nut, push them inside the box. They're not landing on the terminal of the light. Terminals of light. Any question, guys, about this? Yes, Aaron? One more time.
I was just saying, they're just going through the switches, they're not going through.
Yeah, they are carrying the travelers. They're tying the travelers together. But this is actual physical mechanical wiring. That's how you do it. Cool. Any question, guys? Can I have thumbs up, Chad? We fully understand that? Okay. So that's basically the rest of them, guys. I would like you, please, to go ahead and wire the rest of them. And for those of you who want to actually physically mechanically go wire it, let me know. We have a lot of MC cable in our lab that we can make this happen. Wiring with conduits and wiring with wires. There you go. So these are the rest is the examples with wiring with cables and conduits. Any questions for Chad? Any comments? Any questions? Okay. Let me give you guys 5 minutes. And do you allow me to do the branch circuit, just the branch circuits today? Cool. Just do a branch circuit. Thank you.